They're engineered with the utmost seriousness and manufactured with unprecedented precision, all in the pursuit of play. But whether hit, rolled, slammed, or driven to extremes, they always bounce back for more. Now, balls on Modern Marbles. Balls. They spin through our lives in predictable ways, so much so that we take their performance for granted. But the fuzzy, pebbled, gleaming, dimpled surfaces on most modern balls conceal an impressive history of research and development. One ball, however, is a bit of a throwback. Befitting its smash-mouth sport, the football is forged from the basics: cowhide, sweat, and perseverance. At Wilson's Ada, Ohio plant, most of the employees are veterans who have been on the job for at least 2 decades, cutting, stitching, turning, and lacing footballs for the National Football League. But they make more than just NFL balls.
We make them for colleges, high schools, we make them for the youth leagues, whether it be midget, pee-wee, or the junior high. We make between 3,000 and 5,000 balls here every day, Monday through Thursday. Somewhere around 800,000 balls will be made this year.
The plant will produce about 30,000 balls for the NFL each year, a little less than 1,000 for each of the 32 teams. A pro ball begins with cowhide that has been dyed, pressed into a pebble grain for gripping, and treated with a resin-based material to give it a tacky texture. Still, quarterbacks feel the need to rough up a new ball.
When you get a football and it's brand new, it comes with a kind of a slick film. You just want to take it and throw it into the ground a couple times and just rub it in with a little water and make a nice tack on the ball.
A football starts its life in pieces. Each hide provides enough leather for 13 to 14 balls.
All the balls we make here have to weigh a particular weight. For example, the NFL weighs between 14 and 15 ounces.
An NFL ball that's too light or too heavy will end up in a store, not a pro game. The Wilson and NFL logos are heat stamped at 400 degrees Fahrenheit from foil decals. Next, plasticized cloth linings are machine stitched to the panels.
The lining is what gives the ball its strength and shape. It's not the leather, because the leather can shrink or grow depending on the kind of weather we're having outside.
The balls are stitched inside out so that the stitching won't show. They're then turned right side out by a ball turner who will turn between 500 and 600 balls in a day.
The reason we put it in the steam box is to give the leather more pliability where it's softer and a little easier for us to turn. But you got to use a lot of body weight. Your body to do the work in the bar. It's harder than muscles, harder on the arms, shoulders, but at the end, it's all the same.
Next, a polyurethane bladder is inserted. The air hole is pulled through, snipped, and the bladder is partially inflated. A lacer then laces the ball. They work at a pace of 300 balls a day. The laces function as a grip area for a quarterback.
You want to anchor one finger on the laces so that you can torque the ball and spin it out when you throw it. The main thing is to hold the ball in your fingers and in the thumb. Not too tight, not too loose, but just a firm grip. That becomes important when you throw the spiral because you want the fingers to leave the ball consecutively, pinky first, ring finger, middle finger, and then pointer finger is the one that torques and spins the ball and makes the spiral.
The spinning causes a gyroscopic effect, preventing the ball from tumbling or wobbling, which would increase aerodynamic drag. The spiral stabilizes the ball in the orientation with the least air resistance. Football, a game which evolved from soccer and rugby at American colleges in the 19th century, originally used an unwieldy oval ball. The game didn't even allow the forward pass until 1906. In 1935, with the advent of a smaller pointed ball, the modern passing game was born. At the Wilson plant, the ball gets a final forming under pressure.
Each ball starts with about 5 pounds of pressure when we put it in this little cavity, and we're going to put in about 100 pounds of air in the ball to conform it to that cavity to smooth out the seams of the ball.
Finally, at 13 pounds of pressure, the most perfect balls are ready to be used in professional football games. This idea that balls should have a uniform shape, or even that games should have consistent rules, is a modern concept.
In antiquity, balls were used for rituals, and they were mostly rituals of fertility that signified the rites of passage between the winter season and the summer season.
The Mesoamerican game of Pocatawk, that flourished more than 1,000 years ago, was a team game played with a solid, heavy rubber ball. For the Mayans, the game may have had many meanings, as ritual reenactments of wars, or as a way to play out seasonal struggles, with the ball representing the sun. Pocatawk games would sometimes end in a sacrifice from the losing team.
The sacrifice was the decapitation of the captain, which would now release the head from the body, and you would have the ball. And sometimes that skull would be the center of the ball, and then the ball would be built around it.
By the Middle Ages in Europe, some balls were being made from inflated animal bladders covered in hides. They were used in a violent territorial game known as camp ball, from the word camp, an Anglo-Saxon term for battle. The ball had to be moved into the opponent's end of town. Whole neighborhoods battled. The game lasted entire days, involved hundreds of men, and featured hand-to-hand combat that often resulted in serious injury or death. Over time, this destructive game was moved out of towns onto fields, and by the 17th century in England, it evolved into soccer and rugby. Once these games crossed the Atlantic to the United States in the 19th century, they evolved into American football. But it's soccer, with its European origins, that has remained the world's most popular game.
Move in a hurry.
The earliest soccer balls were irregular in shape because they depended on the size and shape of the pig's bladder from which they were made. Leather coverings were introduced later to help the ball keep its shape.
The field wasn't a flat field either. The surface wasn't anywhere like the surfaces today, so that the ball would bounce crazily. Because the ball wasn't round wasn't a problem, because the surface wouldn't let a good ball bounce correctly.
Soccer began to roll toward uniformity with Charles Goodyear's discovery of the vulcanization of rubber in 1839.
Vulcanization is a heat and chemical process that takes a naturally occurring tree sap rubber and gives it a firmer, moldable consistency that actually allows it to form into a shape and hold that shape.
In 1855, Charles Goodyear designed and built the first soccer ball made of vulcanized rubber panels glued at the seams. In 1862, Richard Linden, a shoemaker from Rugby, England, designed the first inflatable rubber bladder, and the basics of the modern uniform mass-produced inflatable ball were born, like this ball from the 1930s.
We have a bladder, and you can see the neck that was on it. The neck sticks out. This is why not only soccer balls were laced in this day, but why a football was laced. They had this neck that had to be pulled out, attached to the pump, the air blown in, and then they'd take a string or something and crush this to hold the air in, tuck it back underneath the leather, and lace the ball back up.
Once soccer began to appear regularly on black and white televisions in the mid-1960s, something had to be done about the tan ball that appeared gray and got lost against the background.
That's when this ball's developed, the black and white ball made of pentagons and hexagons, which is now very visible on TV.
Adidas designed the black and white ball for the 1970 World Cup. The design, 12 pentagons and 20 hexagons, echoed Buckminster Fuller's geodesic domes, which were becoming popular at the time. Still, this ball made from leather, which gets heavy when wet, is a naturally irregular product, and it requires stitching that can stretch unevenly. Adidas's 21st Century World Cup ball overcomes these issues by trading leather for waterproof polyurethane panels that are thermally fused together.
Unlike previous balls where the panels were flat and drawn together into a sphere by the stitching process, these panels are formed in a curved form, so that before the panels are put together, they're already in the curvature they need to be to make a round ball. Therefore, it will more likely do what the kicker intended. I like these new balls. They're kind of neat, but it's still about the players in the end.
Though players dominate sports, balls often get a surprising amount of scrutiny. None more than the ball that is increasingly hit out of the park in America's game. Is it juiced? Wound too tight? Inside, it's got a story ready to be unraveled.
The home team must provide the referee with 24 footballs for each National Football League game. This Modern Marvels fact is brought to you
to sing a song.
Return to balls on Modern Marvels. Baseball. It's a game of statistics, precision, and most of all, tradition. But the ball in play in the major leagues of this most American of games is not made in America. Though they're made of U.S. supplied materials, Major League balls are manufactured only at Rawlings Baseball Plant in a country where soccer is king, Costa Rica. While the game of baseball may be lost in translation in this Central American nation, some of its spirit is alive and well at Rawlings, where the ball sewers' weeks are measured out in baseballs.
They have an incentive that if they meet their quantity, they get to go home as soon as they meet it, and they get paid the full week. And they have also the option to stay and get extra if they continue sewing, up to a 30% of their salary extra.
A ball sewer sinks the first stitches deeper into the ball to anchor them. The sewers use a two-handed motion for greater efficiency.
You use two needles, then you thread them, and then you wax them so you can make a ball faster. Then you put them in the center with this tool, and you pull the needles, and you make the ball.
Rocio Gamboa is one of the fastest ball sewers in the plant. Her secret? Staying competitive.
I have the clock to keep track of time, making it a competition. The fun thing is to try to take less time with each ball. It's a type of a game. I have fun with that.
Though many companies, including Rawlings, have tried, none have succeeded in automating the ball sewing process. It takes 11 weeks to train a sewer to make even uniform stitches. And as any baseball pitcher will tell you, those stitches or seams are the key.
Basic curveball, all you want to do, you can grab it, middle finger up against the seam, create the friction against the seam. All you do is cock your wrist in like that and come right over the top of the ball, spinning it off that seam to create a downward rotation. And physics takes over and the spin will make the ball drop.
The topspin forces the top half of the ball into air resistance, while the bottom half of the ball is spinning away from that resistance. Air pressure above the ball is greater than below, so the ball curves downward as much as a foot or more as it travels to the plate.
It's all about arm angle. 12-6, you're going to be throwing it right here straight down through the ball. And it's very rare to have a true 12-6 curveball. A lot of people throw from a little lower 3/4 angle, so you're going to get more of a sweeping effect on the ball.
All professional baseballs have to fall within the major league specifications to weigh between 5 and 5.25 ounces and to measure between 9 and 9.25 inches in circumference. These specs have been in place since 1872. From the inside out, the modern ball's components are a center pill of cork surrounded by 2 layers of rubber, 3 yarn windings, 1 cotton thread winding, a latex adhesive, a cowhide cover, and red thread stitching. In the early days of baseball, not much about the game was consistent. Neither the ball nor the rules. Clubs bought handmade balls with rubber cores, yarn windings, and horsehide covers from cobblers or tanneries, or made their own.
This is a handmade baseball, circa 1860s. It has the typical, what we call now, lemon peel seam. So you have a single piece of leather here that's seamed up to a point at the top. By the mid-1870s, with the formation of the National League, a gentleman named A.G. Spalding, who was a star baseball player, quit baseball at the peak of his career to move into the manufacturing field. And he founded the Spalding Sporting Goods conglomerate that still exists today. One of his first real coups was to be awarded the official baseball of the National League. The National League was not paying him. He was paying for the rights to brag, and then he could sell his baseball to lots of other people.
Early balls had a rubber center. In 1910, this was replaced by a lighter cork core. To compensate for the weight change, additional yarn was wrapped more tightly around the core, and the ball became livelier. By the mid-1920s, that cork was protected with a double layer of rubber.
That was introduced in the 1925 season, used in the 25 World Series, and then throughout the 26 season, and actually, essentially, that's the same type of baseball that's used today.
Rawlings took over the Major League Baseball contract from Spalding in 1977.
We're producing 2.4 million baseballs a year. That's about 50,000 balls a week, 10,000 a day.
Most of the ball is made up of 3 yarn windings and 1 cotton thread winding. Rawlings keeps the automated winding process secret because they've built machines specifically for Major League Baseball. What's not off limits is the outside of the ball. Since 1974, that covering has been made of cowhide, not horsehide, which had become too scarce in the automobile age.
What they're doing is using the clicker machines and a die going around the covers and going around only the best parts of the leather.
Once the balls have been sewn inside their covers, they're rolled in a press to flatten the seams, inspected, tested for metal from broken needles, stamped with the Rawlings and Major League Baseball logos, and boxed. But if you caught a foul ball during a Major League game, it wouldn't look like this. Before games, umpires rub the balls with Lena Blackburn's rubbing mud to scuff up the ball's surfaces, making them easier to grip. The mud comes from a tributary of the Delaware River. The bounciness of the ball is checked by firing it into the same ash wood that is used to make baseball bats. The velocity of the rebound is then noted, and a ratio, a measurement of the ball's liveliness, is determined. The people at Rawlings have been measuring the ball's rebound since 1977. And according to them, despite ongoing public debate, the ball isn't juiced. Its liveliness has remained unchanged. What has changed over time is the duration that a professional ball is in play. In the 19th century, balls were expensive, and a single baseball was played for an entire game. Today, at many levels of the sport, the ball is often given to fans for promotional reasons. In the major leagues, a baseball only lasts 6 pitches before it's taken out of play. In some ways, the baseball itself has become one of the game's best ambassadors because it's remained relatively unchanged. But the bowling ball has revitalized its sport by undergoing a radical redesign. In 1934, Babe Ruth paid $20 to buy back his 700th home run ball from the fan who caught it. In 1999, Mark McGwire's 70th home run ball of the year sold for $3 million at auction. Balls will return. Marvels. A bowling alley. It looks pretty much the same as it did in decades past. Friends milling about, talking, drinking, eating, and bowling. There's something reassuring about all this sameness, but it's a lie. Out on those lanes, a revolution is actually taking place. Over the last few decades, the number of perfect games bowled, a score of 300, has risen dramatically. The source of this runaway inflation? The ball is juiced. It won't bowl for you, but it'll make a good bowler a lot better. It's all about putting the ball into the pocket, the space between the head pin and either of the two pins right behind it.
What you want the ball to do is actually make a turn towards the pocket. Now what they found is that a larger entry angle into the pocket actually creates the higher probability for creating strikes. As it enters into the pocket itself, the ball actually dances around the pins once it hits it, and it actually allows the ball a greater chance of being able to intermix into the pins, causing them to scatter around.
The lane itself makes hooking the ball hard. The front two-thirds are coated in a layer of mineral oil. This protects the lane from ball impact, but diminishes a bowler's control. To make a ball that can roll straight through oil and then still hook sharply just as it gets to the pins, you need complex chemistry on the outside and sophisticated physics inside.
You can think of a bowling ball as having a core and a shell. You can think of it just like the Earth. It has a core in it. There are different layers of the core, and then there's the outer part, which we call the veneer.
Prior to the 1980s, bowling balls had spherical, symmetrical cores that did little to help a bowler put hook on the ball. Since then, designers have developed solid asymmetrical cores placed at the center of the ball that have increasingly helped steer it.
We can actually literally put a steering wheel inside of the bowling ball to get it to behave the way we want it to behave.
But how do asymmetric cores help steer the ball? Depending on where the finger holes are drilled on the surface of the ball in relation to this core, a pro shop can reduce the spin for someone inclined to high revolutions and add more to a low spin bowler's ball. In addition, with each revolution of this ball, the core is altering the spin slightly so that a fresh part of the ball comes into contact with the oiled lane.
You can see these lines here. These lines are oil. Every rotation is a different line. What that means is that as the ball goes down the lane, it's seeing a fresh surface. What you get is a ball that is very aggressive down the lane when it sees friction, because down the lane it's dry, so it makes an aggressive move.
In addition to steering, cores of different densities vary the weight of the balls, from 6 to 16 pounds. All bowling balls have a uniform outer dimension, 27 inches in circumference. Heavier or lighter mineral fillers create cores and ultimately balls of various weights.
We take the polyester resin, we mix it in with mineral fillers, we blend that up into a milkshake type mixture.
With the help of a catalyst, this mixture goes from liquid to solid in 2 minutes and is then removed from the core mold. The core is drilled so that it can be mounted on a pin in another mold.
We fill that area with a polyester resin, a very light, low-density product that goes around the outside. We're pouring a core every 12 seconds all day long. These go onto a rack and have about a 45-minute cure period.
The high-tech core's pocket-seeking mission is aided by an outer shell, or veneer, made from a high-performance urethane, a porous additive-enhanced resin that has improved traction over the hard, smooth polyester balls of the 1970s. This veneer can be applied to the ball in almost no time.
We take that large core with a hole in it, we suspend it on a pin inside a mold, and then we pour the shell around it. This is a very violent chemical reaction. This goes from a completely liquid state to a completely solid state in less than 30 seconds.
What we've done with that urethane polymer is actually created a kind of a chemical cocktail. We actually can create a rigid, porous type material. So it's like a polymer sponge.
So the ball soaks up oil as it cuts through it. As a result, it creates friction earlier and produces a sharper hook before reaching the pins. Once the veneer has been applied, the balls go into giant grinders that trim and smooth them to size. Logos are then etched and painted. Then the balls are given a sanding for a final finish. Not surprisingly, older bowling balls were fairly unsophisticated. Though bowling has ancient origins, the clearest antecedent is a German ritual called Kegel, which originated in the 4th century and used a stone ball. The modern form of the game moved indoors in the 19th century and featured the first manufactured bowling balls.
Earlier on, bowling balls were made out of wood. This is actually from the early 1900s, late 1800s. Most of those bowling balls were made out of lignin vita. Common name for it's like ironwood. And it's a very dense, hard type material.
The next breakthrough came in the early 19th century, the rubber bowling ball.
Hardened rubber has got the term ebonite material, and that's basically where our company name is generated from, is that term hard rubber.
Over 100 years old, the Ebonite company has seen every advancement of ball technology. But just how much hook can enhanced physics and chemistry put on the ball? We've got an expert bowler, Chris Muldrow, who will throw 2 different balls exactly the same way. The difference in performance is in the balls.
The first ball we're going to look at is a polyester ball. What you're going to see from the polyester ball is a very, very straight trajectory, not a lot of hook. The problem that the ball faces is that it's so smooth and so slick that it can't create friction in the back end of the lane. As a result of that, the ball never gets into a hooking motion that he's trying to create.
In addition, the ball has a spherical core that is essentially neutral. It doesn't help the ball hook.
The difference between that ball and most of my other balls is that it's like a weaker shell and a weaker core, so it goes very straight.
The second ball is a high-performance ball with an advanced cover and core.
Now what you have is the perfect match between a core that wants to make the ball hook and a cover that wants to make the ball hook. So in this shot, he'll strike.
But no matter how much care goes into a bowling ball, there's always some guy who just has to do it his way. There's another ball that shares the advanced physics and chemistry of bowling balls. The secret to its aerodynamics was discovered by accident. Today, it's being engineered to fly farther than ever. In 1955, there were only 270 perfect games bowled. In 2005, there were 56,212 perfect games bowled. Balls will return. On Modern Marvels, we now return to balls on Modern Marvels. A golfer strikes the ball. The ball leaps into flight. The whole action is over in a moment. It all seems so, well, simple. The physics are anything but.
For me personally, I want the ball to launch in the 10 to 12 degree range and spin about 2,500 RPMs.
But who can keep track of launch angles and tiny white golf balls spinning thousands of revolutions per minute? The men and women of Callaway Golf. That's who.
Behind me is the indoor test range at Callaway Golf. It is a machine that launches a golf ball down a 90-foot corridor of strobed cameras at very specific spin rates and velocities under very controlled and measured environmental conditions. We can parse the trajectory into distinct segments and determine the aerodynamic forces acting on the ball at this variety of speeds and spins.
Why do this? It's all in an effort to build a golf ball that will fly farther. Because in the marketing of golf balls, distance matters.
There's three things that are most important to a golfer. It would be distance, distance, and distance. And even a professional golfer would tell you that if you gave them the same spin and the same feel, the same level of durability, and you could give them 3 more yards, they'd take it in a heartbeat.
So how do you make golf balls that are hard enough to fly hundreds of yards, but soft enough to be spun and controlled around the greens?
We're cutting open a 3-piece golf ball, but if you look really close, you'll be able to see the rubber core, an ionomer boundary layer, and a very thin urethane layer on the outside of it that allows this golf ball to become a distance ball because of the high speed of the core, the high speed and the low spin of the boundary layer, and then the really soft urethane layer on the outside allows a player to spin that golf ball.
Small, refined-looking golf balls start with the same ingredient found in car tires.
So this is the main ingredient in a golf ball center. It's called polybutadiene. It's a synthetic rubber. It is the liveliest or most resilient rubber that we know of, and that's why it is in golf ball cores. Okay, we're standing on the mezzanine of the Banbury internal mixer. Much like a dough mixer or a cake mixer, it has 2 huge rotors inside, and it takes the rubber and all of the chemicals, the other powders, and mixes them together. It's an 800 horsepower machine, mixes 530 pounds of rubber and chemicals at one time in about 6 minutes.
These batches are squeezed out in a 100-inch mill, cooled, checked for consistency, and then extruded into pellets to be formed into golf balls.
You're taking slugs of rubber or preforms. They're hand-loaded into a compression molding press, and then under heat and pressure, they form the golf ball cores.
After being formed under 500 tons of pressure at 335 degrees Fahrenheit, these cores are cooled and ground into perfect spheres. The cores are then fed into an injection molding machine to be covered with a dimpled surface.
The injection molding machine forces the molten plastic around the cores. Inside each individual set of cavities, the core is resting on a set of pins. And as the material flows around, just before it's complete and just before it hits those pins, they retract. And the rest of the ball is then filled in. The pins are there to hold the core precisely in the center of the mold.
From there, the dimpled balls are milled, polished, painted with a primer and finish coat, dried, and then ink stamped with a logo. These pristine golf balls are far removed from their ancient predecessors, lowly stones. The game's origins lie with European shepherds from the Middle Ages, who used the crooked ends of their staffs to drive stones at targets and down rabbit holes. A 14th century German law indicates an early obsession with distance. A shepherd was permitted to graze his sheep as far as he can drive a pebble with one strike of the staff. The game was most popular in Scotland, where in the 15th century, the first golf balls appeared. They were made of wood.
And they probably weren't very playable by today's standards. The wood golf ball is going to feel relatively hard, probably didn't spin a lot off of the club, so it was a relatively low trajectory, kind of boring.
The next bounce forward for the golf ball came in the 17th century with the invention of the feathery.
It's a leather sack that's stuffed with wet goose feathers and wet leather, and when it dried, the leather contracted and constricted those goose feathers, and it became a relatively firm, hard little ball. But aerodynamically, it still wasn't very good, and you probably couldn't spin that ball around the greens very well.
In 1848, the feathery was replaced by the gutta percha ball, made from the rubbery dried sap of the Central and South American sapodilla tree.
Gutta percha golf balls, again, were smooth and didn't fly very well aerodynamically. What they found was, as the ball got old and nicked up, it started to fly better. And they realized that the nicks on the golf ball had something to do with aerodynamics.
So the revolution in golf ball design, the discovery of the dimple, was made accidentally by 19th century golfers.
And they started molding patterns onto the ball. Dimple patterns and bramble patterns and sometimes geometric shapes to improve the aerodynamics of the golf ball. what happened with every one of these golf balls is they got better from a distance standpoint and a feel standpoint and a spin around the green standpoint, and with that advent of dimples on them, they became better aerodynamically.
How does a lowly dimple have such a dramatic effect on aerodynamics? The dimples create a boundary layer of energized air that allows the ball to cut through the air with less drag, which is a disturbance behind the ball. Drag would slow the ball down.
That boundary layer, if it's energized properly, will stay stuck to the ball's surface and warp around the ball, minimizing the disrupted state behind the ball, or the wake region behind the ball.
All balls have dimples, and to the naked eye, look the same. So to really measure the distance difference between two balls, you'd need to hit them exactly the same way time after time. No human can do this.
This is an extremely repeatable robot. If we set up a driver in the robot's hands to impact a certain location on the club face, we expect that that location will maintain its position within 0.3 of 1 millimeter. We expect that whether or not the club is being swung 10 to 100 to 1,000 times, that the impact speed will only vary 1/10 of 1 mile per hour.
The robot repeats a drive on 2 Callaway golf balls, a top-of-the-line Hex Tour and the less expensive Big Bertha ball.
When we go from a 3-piece golf ball to a 2-piece golf ball, we see a drop in ball speed, an increase in launch angle, and a decrease in backspin.
Which all adds up to this. You spend a couple extra bucks, you get a couple extra yards. Finally, in the midst of so much complexity, a little simplicity. Meanwhile, although the tennis ball's design looks simple, its manufacture is surprisingly complex. In November 2006, a Russian cosmonaut hit a golf ball into Earth orbit from the International Space Station. In its first 3 weeks alone, it traveled more than 10 million miles. And presto, you've got a tennis ball. What could be easier, right? Not exactly. Sure, they're cute and fuzzy, but they're also tough enough to take a pounding. The tennis ball deserves a little respect. And at Penn's manufacturing plant in Phoenix, Arizona, that's exactly what they get.
I used to be a quality manager for an aerospace company that installed wiring into jets and airplanes. And when I came here, I thought it would be a much easier process. This really is far more complicated than that process.
In a week, this facility will pump out 1,700,000 balls. The last tennis ball company still manufacturing in the United States, Penn has been able to stay put because of innovation and technology.
The reason we've invented a lot of the machinery you see around me in the facility is to be able to control costs. Because if we can't control costs, we'd have to close down this facility.
A tennis ball starts with a natural product, Malaysian rubber, mixed with 11 chemical ingredients.
This is the auto compounder. This holds all the ingredients that go into the tennis ball core. Each one of these chutes will contain a different ingredient.
Like sulfur, to accelerate the curing process. Suprex, a filler that adds bounciness. Tactine to give the rubber some tackiness, as well as some oil to lubricate the mix and move it through the process. The auto compounder can generate 21 different chemical blends to make balls for different playing surfaces, like clay, grass or acrylic courts, indoor or outdoor conditions, and high altitude.
What the balls are designed to do is play the same way whatever surface you're playing on. The best ball is one you don't notice. You don't want it to be too lively, you don't want it to be too soft. If at the end of your match, you don't even mention the ball, we've done a good job.
Once the rubber is mixed, the extruder pumps it out as pellets that are loaded into molds. At temperatures of up to 325 degrees Fahrenheit, they're formed into halves of the tennis ball's cores. Glue is then applied to the rims of the hemispheres, and they're off to the second cure.
The two halves are bonded together in second cure. The temperature is anywhere from 300 to 325. Also at this point, the pressure is applied inside the core.
As the halves are joined, the mold seals in a pressure of approximately twice the Earth's atmosphere at sea level. This pressure, double that of a football, helps make tennis balls bouncy. At this point, the ball looks somewhat like its most direct ancestor, the lawn tennis ball. The game of lawn tennis was first played in the 1870s in England, on grass with a rubber ball that was hit back and forth across a net. But the ball was hard to control, so the English covered it with flannel to give their rackets a more grippable, controllable ball surface. On Penn's modern ball, woven felt, a combination of New Zealand wool and nylon, protects the core, reduces bounciness, and slows the ball in the air to playable speeds. Originally white, tennis ball felt has been dyed optical yellow since 1972 to improve visibility on the court, and just as importantly, to make it easier to spot on color televisions. The felt is cut into dumbbells that in pairs will cover the surface of a ball. In order to stick to the rubber core, the felt is coated with glue on the back and edges and loaded into automatic felt placement machines where the balls get their fuzz.
It'll feed the core in. It'll come up on a little post. 2 needles will hold the felt. Another roller will come through with needles on it. It'll roll that piece of felt off. That'll be placed in a car that will travel to the core. They'll come in from each side and place the felt onto the core. From that point, it'll go through the roll down, which will roll the felt onto the core to try to get rid of any wrinkle or blemish on there.
In the third and final cure, the felt is bonded to the ball at 325 degrees Fahrenheit for 12 minutes. The visible seams are actually a line of glue.
The next step after third cure is the fluffer. And what that does is it fluffs up the nap so the felt isn't compressed to the ball after it comes out of the mold. The next step we call the vision machines. That's where it places the logo on the tennis ball. Places it in the exact same spot each time, and that's where it'll stamp the logo.
Balls are constantly tested at the plant to make sure that they meet United States Tennis Association and International Tennis Federation specs. Balls are checked for size, weight, bounce, and durability.
The test, we put 8 balls in here. The test lasts for 60 minutes. It hits the ball against a steel target. It goes at between 110 and 115 miles per hour, checking for core breakage or felt lifting.
All this care goes into creating a uniform ball. But still, during a match, you'll see a server selecting certain balls over others.
If you're serving, you want the ball to move much faster on the serve, so you're always looking for the newest ball, the most compact ball.
You want a faster ball, I guess a newer looking ball. Because when the balls are, out of the can, they really bounce high and you can hit them harder and the ball goes faster.
This instinct is correct, but it doesn't have to do with ball pressure. Rather, it's the aerodynamics that matter. In the air, the condition of the felt impacts air resistance or drag. As a new ball is used, the felt fluffs out. The more porous it becomes, the greater the drag as air passes through it. Though they're built to last, the balls are inexpensive enough to be replaced after each session of play.
The life expectancy in the United States is 1 session, and whether that's 1 set, 2 sets, 3 sets.
Used tennis balls end up becoming practice balls, or they're simply thrown to the dogs. And perhaps this really is the trajectory of the ball through human history. Once sacred objects, balls have become, in some cases, inexpensive enough to be virtually disposable, tossed to fans or pets. But hey, that's the way the ball bounces. They're super, they're crazy, and they can be found in everything. From carpet to computers, books to boats, automobiles to airplanes. They're essential to mail bonding, reef repair, and cut control. Without them, our material goods would simply fall apart. Now, the stuck-up, tacky world of glue on Modern Marvels. Concealed within our machines and structures is a substance that is essential to their functioning. This hidden ally makes them stronger, cheaper, lighter, even sexier. And it's the least sexy substance of them all, glue. Like Superman's alter ego, Clark Kent, glue goes about its duty unnoticed. But when called upon, it can exhibit superhuman strength.
A properly used adhesive is not apparent to a person using whatever.
Nie, to już nie fajnie tak było, machanie przy dziewczynie.